Let's imagine that we have a magnetic field. This magnetic field might be created by some magnets or something like that. Maybe down here we have some North Pole, and up there we have some South Pole, and they're creating these magnetic fields. These are the magnetic field lines. So whatever's creating them, we're not worried about that. We are just assuming that we've got a magnetic field, and we'll just assume for the time being that it's a uniform magnetic field, a constant magnetic field. In the magnetic field, we have a charge Q. My question is, what kind of force do we think is going to be exerted on the charge? And we can use some analogies to what we had with the force due to the electric field. First of all, we might think, well, the stronger the field, the stronger the force. And that is absolutely true. The bigger the magnetic field we have, the greater the force acting on the charge. So it turns out the force is proportional to the strength of the magnetic field, the magnitude of the magnetic field. What else? Well, what about the charge? It turns out that the more charge there is, the stronger the force. A bigger charge feels a stronger force than a smaller charge. So F is also proportional to Q. But keeping in mind, we are talking about a vector quantity, the vector force. It turns out the magnitude of the force only depends on the magnitude of the charge. A positive charge feels just as much force as an opposite negative charge. The sign comes in to the direction. So we'll need to take the sign into account when we figure out the direction of the force that acts on the charge. Well, if this were the electric force, that's all that it would depend on, the magnitude of the electric field and the magnitude of the charge. However, the magnetic force depends on something else. It depends on the velocity of the charge. If the charge is not moving, it doesn't feel a force. So let's imagine that our charge has some velocity v. It turns out that the faster the charge moves, the greater the magnetic force that's acting on it. That's a very, very surprising result. The force actually is proportional to the speed. The faster it's moving, the greater the magnetic force. But it also depends on the direction of the velocity. If there is an angle between the magnetic field and the velocity, and we'll call that angle theta. Now let's remember, how do we determine the angle between two vectors? We have to put them, let me make two vectors here, we have to put them tail to tail. To determine the angle between two vectors, let's say here's the velocity vector, here's the magnetic field, how do we determine the angle? We don't put them head to tail. We put vectors head to tail when we want to add them together. To determine the angle between them, we put them tail to tail. And then the angle between them is always the smallest, closest angle between the vectors. So the force then depends on the angle as the sine of theta. The force is actually proportional to the sine of the angle between the velocity vector and the magnetic field vector. That is a very, very peculiar, surprising result. I'm going to write this as an equality, and the fact is we do not need a constant of proportionality in here. We can think of the units that we'll define for b actually make that constant equal to 0, so we don't need to worry about that. The force we'll write as an equality then, that Q equals, and I'm going to write these in a particular order. We know that A times B is the same as B times A, as long as we're talking about scalars. So the order when you multiply things doesn't matter, but I want you to kind of remember this in this order because it's actually going to help us later on. So the force equals Q, and remember it's actually the magnitude of Q, because we're talking about the magnitude of the force. This has to be a positive quantity. The magnitude of the force, magnitude of Q, VB sine theta. There we go. F equals QVB sine theta. But remember, that's really the magnitude of Q. One more quick point about theta, the angle between two vectors. So let's just think about that just for a second. If we've got two vectors that are in the same direction, we put them together, what's the angle between them? 0. As they get further apart, we get 10 degrees, 20 degrees, 30 degrees, 45 degrees, 90 degrees, 100 degrees, 110, 120, 130, 150, 160, 170, 180 degrees. So two vectors pointing in opposite directions have an angle between them of 180 degrees. If this continues to move over this way, the angle is not larger than 180 degrees. The angle is now measured this way. So the angle is always measured the shortest angle between the two vectors. So we have 90 degrees, 100 degrees, 180, but then it's back to 170, 160, 90 degrees. So these are 90 degrees apart, these are 90 degrees apart. The orientation doesn't matter. Remember, the angle is always measured in the shortest, closest way to go from one to the other. So angles between vectors, theta, can have a minimum value of 0 to a maximum value of 180 degrees. So theta is greater than or equal to 0 degrees, or less than or equal to 180 degrees. We'll never have an angle theta that's larger than 180 or that's negative. 0 is the minimum value, 180 is the maximum value. Very good. Let's stick some numbers in here. What units do we have for the magnetic field? Well, taking our force equation, F equals QVB sine theta, dividing by the QV sine theta, we have that B is equal to F over QV sine theta. So the units of B must be equal to the units of F divided by the units of Q, the units of V, units sine theta. Well, what are those? What are the units of F? The standard SI units of force are newtons. Standard SI unit for charge, coulombs. Standard SI unit for velocity, meters per second. Standard SI unit for sine theta, that's unitless. I don't mean what are the units of theta, radians or degrees, but sine of an angle is a unitless quantity. So sine theta has no units. So we have the units of B will be a Newton per coulomb meter per second, or bringing the second up to the top, we can write this as a Newton second per coulomb meter. Or we know that a coulomb per second is an amp. We could also write this as a Newton per amp meter. There we go. This combination of units, once again, is something that we're going to see often enough that it has its own name. 1 Newton per amp meter is called a Tesla. Tesla, named after the very famous physicist Nikola Tesla, also the car Tesla. It's not named after the car Tesla. The car Tesla was named also after Nikola Tesla. But the standard SI unit that we will use for the magnetic field is the Tesla, and we will write that as 1 capital T for short. Very good. Now let's go back to our equation. F equals QVB sine theta. And let's think about that for a second. What if the magnetic field is 0? How much force do we have on the charge? Well, with no magnetic field, we have no force. F equals 0. That makes sense? No field, no magnetic force. What if the charge is 0? Well, if Q is 0, again, we have 0 force. That means that we will not have a magnetic force on neutral charges. We have to have a charged particle or a charged object in order for this force to give us a non-zero value. We have to have a charged particle. What about if V is 0? If V is 0, again, we get 0 force. What does that mean? That means even if we have a charged particle in a magnetic field, if it's not moving, we have no force. The force is only exerted on a moving charge. So if v is 0, F is 0. What if theta is 0? Sine of 0 is 0, so again we get 0 force. What does that mean, 0 theta? Remember, theta, let's back up for 1 second, and let me emphasize a point that I've mentioned before, and it bears repeating because this is very, very important. We have this equation, F equals QVB sine theta. In order to use that equation, it is essential that we understand what every single quantity in that equation means. Let's just go over that for a second. What is F? F is the force on a charge. What is absolute value Q? That is the magnitude of the charge that we're talking about. What is V? It's the velocity, it's the magnitude of the velocity of the magnitude of the velocity that the charge has as it's moving through the magnetic field. What is B? B is the magnitude of the magnetic field. And what is theta? Theta is the angle between what? It is the angle between V and B. So we've got some velocity of the charge V, whatever it is. We've got some magnetic field B, whatever it is. Theta is the angle between V and B. V and B. This angle here. Whenever you use this equation, make sure you keep that in mind. The hardest part in this is to remember what theta is. Theta is the angle between V and B. If theta is 0, what does that mean? It means the charge is moving in the same direction as the magnetic field, so that V and B are in the same direction. If V and B are in the same direction, if the particle is moving along the magnetic field, we have 0 force. What if theta is 180 degrees? What does that mean? That means the charge is moving in the opposite direction to the magnetic field. So if we've got a magnetic field this way, the velocity must be this way. They are in opposite directions, 180 degrees. What's the force in that case? Well, sine of 180 is also 0. So in that case, again, we have 0 force. If the charge is moving along the magnetic field or opposite the magnetic field, we end up with 0 force. What about theta is 90 degrees? Theta 90 degrees, sine of theta is 1. That's the maximum value that sine theta can have. That means the amount of force that we're going to get is the maximum amount of force for that particular direction. That means, what does it mean to have theta equal to 0? The charge is moving perpendicular to the magnetic field. In that case, the force that we get is the maximum force for that direction. Any other direction will give us less force. Very, very good. Let me just mention one more thing before we move on, and that is, let me come back to this unit here. The Tesla is a very large unit for magnetic field. Sometimes a smaller unit is sometimes used, and that is called the Gauss. 1 Gauss. A Gauss is much smaller than a Tesla, and it's actually equal to 10 to the minus 4 Tesla. So it's a much smaller value. But because Tesla is such a big magnetic field, Gauss are actually are often used to measure ordinary magnetic fields. Great. Now there's one more thing that we have not talked about. We have talked about the magnitude of the force, the magnitude of the magnetic force acting on the charge. One thing we have not talked about is what? The direction of that force. Remember, force is a vector. We've defined the magnitude of the vector. What is the direction of that vector? Well, that is a little bit tricky. This is very peculiar with all the velocity and the direction involved. The force, the direction of the force is very peculiar.